Welcome to the math jungle. We're ready to dive in and we're going to tackle some monster transformations with regards to exponential functions. Now, before we move any further, I want to just be crystal clear as what exactly is a transformation. So we want to talk about some of the subtopics that fall under this larger umbrella that we call transformations. And the first one, I think the first two we're really good at already. So we'll talk about, we might as well talk about vertical translations. Okay, now translation is different than a transformation. A translation is a subcategory, and a vertical translation is something like saying, let's take f of x and let's add 2. Now, believe it or not, the 2 doesn't always have to fall to the right of the f of x. You could say 2 plus f of x, but the bottom line is we're shifting the graph up 2 units. So vertical translation could go up or down. The second one is a horizontal translation. And in this case, that plus, let's say it's plus 2 again. The difference is, instead of being on the outside like these guys were, we're going to sneak that plus 2 on the inside of the parentheses. And now, do you remember how it's that would go left 2 units? And then if I changed it to x minus 2, it would move it to the right. Okay, so we're really good at those two. The other two that we're not as comfortable with yet is we'll start off with what we call a vertical stretch. And a stretch also could include a compression, so I should also include that here, compression. And what's happening here is the 2 is now a multiple of f of x instead of an additive. And what we would do in this case is we're making the graph twice as tall as it originally was. And the key is for us is that we're going to multiply each y value by 2. And then the last one, the one that I find the most challenging, is a horizontal stretch or compression. Okay, and in this case, again, what we're going to see here is we've got a multiple of 2, but the 2 is on the inside of the parentheses, and it's strictly multiplying the x-coordinate. But in order to graph this function, what we're actually going to do is we're going to divide each x-coordinate by 2. And so we said if this bear here, it actually produces a compression. We're shrinking all of the x's and we're making the graph more narrow. So before we really get specific to exponential functions, I wanted to do just a quick crash course on something we saw a couple months ago and try to review everything we just talked about in the first 2 minutes with this very generic function f of x that we have here that passes through these 3 really friendly points. So let's call this number 1, and I'll try to color code everything that I do here on the screen. Is if I said I want to do f of x plus 3, we're going up 3 units. It's a vertical translation, and let's see, my new graph is going to look like this. It's kind of like parallel in a sense to the original one. The other one to watch out for is what if I wanted to do x minus 3. Now it's inside, it's a horizontal translation, and we're moving to the right 3. And I'm going to always revert back to the original function. So we're going to move everybody, we're going to shimmy them over to the right. And again, it's going to be parallel to the original function in a sense. Let's see, we'll get a little bit crazier here. If I wanted to do, let's say, 2 times f of x, now what I'm doing is this is a vertical stretch, and I'm going to multiply every y-coordinate by 2 units, and I'm going to double everybody's height. So this blue guy, the y-coordinate's negative 2. By the time I double it, I get negative 4. This y-coordinate right here is 5. By the time I double it, I get 10. And this y-coordinate's a 3. By the time I double it, I get a 6. And let's see what this graph looks like. And you can see it got stretched, like grabbing a piece of silly putty and pulling it up and down. Let's see, let's grab a different color here, shall we? Number 4, what if I wanted to do f of 2x? Now it's a horizontal compression, and what we're going to do is we're going to now divide each x-coordinate by 2. And let's see, so this negative 4 right here is going to change to negative 2. 0 is going to stay 0, and the 3 is going to go to a 1.5. And as I was doing that, of course, the y-coordinates remain the same, and that's the new function I have there. Last but not least, I'll throw one more curveball at you. You tell me if you like this one or not. If we did negative f of x, do you remember what impact that negation did? And this is when it's on the outside, it's negating the entire function f, not just one single term. But it was a reflection over the x-axis. So let's see, this point went here, the 5 went down to -5, and the 3 went down to -3, and we got a picture like that. So that's a really quick crash course of all of the transformations we've been exposed to. Now we're going to start to get specific to exponential functions, and before we start transforming them, we want to just make sure that we've got our basics and our fundamentals down pat. And I wanted to see I've graphed two functions already, and I wanted to see if you could match them up. Could you tell me, of the two that are graphed, which one represents 2 to the x versus which one represents 4 to the x? And what you'll notice, if you just look through some of the special points, they both intersect the y-axis at 1, but then the blue graph that goes through the point 1, 2, 2, 4, 3, 8, and you'll notice that that matches up really well with y equals 2 raised to the x. And then the other function, this red one, still got a y-intercept of 1, but then it goes through 1, 4, and then this is supposed to be 2, 16, and that matches up really well with 4 raised to the x. Now off of that, can you guys try to graph y equals 3 to the x? It's going to kind of nestle itself in between those two functions. It's still going to have a y-intercept of 1, and it's going to pass through the point 1, 3 and 2, 9. It also go through -1, 1/3, -2, 1/9, and again, just like these other graphs, it'd be asymptotic to the x-axis. And what I mean by saying that it's asymptotic to the x-axis is I'm saying that it's continuously getting closer and closer as we move towards negative infinity without actually touching the x-axis. And to try to stress that, I'm going to draw a nice dotted line across the x-axis right here, stressing that there's a horizontal asymptote. The equation of this asymptote is y equals 0. And it's just this imaginary invisible line that the graph continuously gets closer to without touching it. So as a base here, we've got this function y equals 2 to the x already graphed for us. And what we're going to do is we're going to use this terminology. We're going to call this the parent function. Okay? And in other words, it's kind of like thinking of it as the original function by which we're going to derive the other functions from. And so I'm going to go kind of quick through some of these the translations anyway, because we're really good at these, like we already said. We're inside the parentheses, so it's a horizontal shift. And what we're doing is we're going 3 units to the which direction? Yeah, we're going to move to the left. And so I'm just going to take each point here and slide him to the left. So like, for instance, this point here is going to go 3 to the left. This guy's going to go over here. This guy's going to go over here. And we're just going to keep sliding these rascals over the best we can. 2, 3-ish. Let's see, 3 there. Okay. And we should get something just like that. Let's see, got to change colors here real quick. This one right here, again, we're on the inside, so it's a horizontal shift. We're going to go 1 unit to the right. And we're just going to take each of these rascals, go 1 unit to the right. Doesn't get any better than this, does it? 1 unit to the right. Love it. And one thing that we're going to stress here is that every time we draw one of these rascals, we should be including the horizontal asymptote. We want to make sure that it is present. I should have done it on the first one here. And what we're going to stress is that when you're sliding graphs or shifting graphs left and right, it doesn't affect this horizontal asymptote. No matter how far to the right or how far to the left you move, it's still y equals 0. So let's see if we can put that last statement in a nice sentence and highlight it in our notebook. And what we're saying is shifting an exponential function either to the left or to the right does not, emphasis on not, affect the graph's horizontal asymptote. Okay? In other words, the asymptote was originally y equals 0, and it is still at y equals 0. Okay, the theme on this slide is going to be vertical shifts. You'll notice that the +3 is outside, -2 is outside. And I'd like to see you use the same terminology in class tomorrow as you're talking about this with your partners. Is the +3 on the inside or outside? In this case, outside. This is my parent function right here by which we're going to build and derive the other functions from. And quite simply put here, we are moving everything up 3 units, okay? So we're just going to take this bear, we're just going to go straight up 3. So notice the y-intercept went from being a 1 up to a 4. And let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, something along these lines. Now, something we have to worry about or talk about now that we didn't in the last example was where is that horizontal asymptote. Now remember, the horizontal asymptote was originally at y equals 0, but now we're shifting everything up 3 units. And so now I've got this nice horizontal asymptote at y equals 3. I have to visibly show that imaginary line and label it as y equals 3. The next example here, we see the minus 2 on the outside. We're going to shift the function down 2 units. Again, I'm reverting back to the original function, and we're going to slide everybody down 2 units. Trying to be as accurate as we can without taking, whoops, that one's going to be a little higher than I initially had it. As accurate as we can without taking forever. Always a nice thing. It kind of, again, it's kind of like almost parallel in a sense. I know we usually save or reserve the idea of parallelism for straight lines, but it's the fact that they kind of mirror each other's behavior. And now this asymptote is at y equals -2. So let's try to summarize what we did with that asymptote. So shifting a function either up or down does affect its horizontal asymptote. Okay. And that asymptote is going to move up or down just like any of those points. If all the points move up 2, the asymptote moves up 2. So right off the bat, what do you think the theme is going to be on this particular slide? Notice we're multiplying the function f of x by a factor of 2, or in this case we're multiplying f of x by a factor of 0.5. And the theme here is going to be vertical stretching or compressing. And the focus is going to be on the y-coordinates. In this case, we're going to multiply all the y-coordinates by 2, and in this case, we're going to multiply them by 1/2. And we're working again off of our parent function, y equals 2 to the x. Now, these points in here, the heights are very hard to get our hands on. I think the height right here is 1/2, and the height right here is 1/4. So we're going to do the best we can. So with this first one, let's say to ourselves, it is a vertical stretch by a factor of 2. And basically what that means in English is we've got to multiply each y value by 2. Or we're going to double the height, really. So the 1/4 became a half, and the 1/2 became a 1. The 1 became a 2. The 2 became a 4. The 4 became an 8, and so on and so on. This 8 here would have became a 16, and function's just really growing a lot faster. Now the question is, what happened to the horizontal asymptote? Well, let me tell you about this. It was originally y equals 0, right? Well, if you double that or multiply that by 2, you still get 0. So in this case, the horizontal asymptote is unchanged. All right, next one. Again, 0.5 is on the outside, so it's a vertical compression by a factor of 0.5. And in English, that means we're going to multiply each y-coordinate by 0.5. So this 1/4 became a 1/8, and the 1/2 became a 1/4, and the 1 became a half. The 2 became a 1. This 4 became a 2. Let's see, this 8 became a 4, and so on and so forth. And it's going to be a much slower function, still increasing nonetheless. And again, the asymptote stayed at y equals 0 because no matter what you multiply 0 by, you still get 0. So undoubtedly you've noticed that throughout tonight's video, one of our major themes is trying to keep track of this horizontal asymptote and just identify whether he's being impacted and moved by the transformation or not. And so a good thing, I think once this video wraps up and you're ready to close shop for the night, just stop and kind of try to summarize which of the transformations do affect the horizontal asymptote, versus which ones don't. So we're going to say here that stretching an exponential function vertically does not affect its horizontal asymptote, and that is simply because when we stretch something vertically, we are multiplying all the y-coordinates, and if you start with y equals 0 and you multiply that by any number on God's green earth, you still get 0. Well, I saved our favorite one for last, and the theme here is what? Our multiples are now inside the parentheses, so our theme here is going to be horizontal stretching or compressing. And we'll get kick-started here. This 2 right here, it indicates that we have a horizontal compression by a factor of 2. which in English means we are dividing. Yes, believe it or not, we're going to divide each x-coordinate by 2. Okay, so for instance, this -2 right here is, by the time I divide it by 2, is going to become -1. And it's important that I try to maintain the same y-coordinate. Let's see, this -1 becomes -1/2. The 0 stays 0. The 1 becomes a 1/2. And notice every time I point to a point, I'm strictly referring to its x-coordinate. I'm trying to ignore the y-coordinate. For instance, this point right here, x-coordinate's a 2, which is going to become a 1. Let's see, this x-coordinate I would guess is like 2.5. So that's going to become like 1.75-ish if I'm estimating. This guy's a 3, which is going to become a 1. Whoa, yeah, I did screw that up. Let's slide that bear over a little bit more. Be like 1.25. So let's see if we can connect these dots here. And the asymptote, believe it or not, is still going to be y = 0, which is good news. The less it moves, the easier our job is. And the reason that is, we're only dividing the x-coordinates by 2, and we're not affecting the y-coordinates. So that's why this is going unchanged, because we're not the y = 0, we're not affecting the y's. Next one, we're going to do a horizontal stretch by a factor of 1/2. In other words, we're going to divide each of the x-coordinates by 1/2. Now, believe it or not, that's equivalent to multiplying each of the x-coordinates by 2. So you could either way. You could either say I'm going to divide every x-coordinate by half, or you're going to say I can multiply every x-coordinate by 2. It's the same thing. You'll get the same result, and you can check that on your calculator. So for instance, this -2 is going to slide over to -4. This -1 is going to slide over to -2. 0 is going to stay 0. 1 is going to slide over to 2. Let's see, 2 is going to slide over to 4, and we'll say 3 is going to slide all the way over here to 6. And look at the stretch that is taking place here. Almost hard to see the curvature early on. It becomes very linear. And again, the asymptote is going to be right at y = 0. It's unchanged. And with that being said, it's worth saying this: stretching a horizontal function horizontally, again, just like the last slide, does not affect the horizontal asymptote. So really, as you look back on all the transformations we've done so far, the only one that really had an impact on the horizontal asymptote was a vertical shift when we were going up and down. So our goal is to now try to mix up all of these transformations and see if we can pick them out and decide which ones are vertical translations and horizontal translations versus vertical stretching and horizontal stretching, and kind of jumble it all together. And let's see, we'll get more practice with this tomorrow, of course, in class, so I might go a touch too fast, but hopefully not. This first one, I've noticed the +4 is at the end, and so I'm thinking that's going to be up 4 units. Here I've got -3. It's attached to the x and the exponent, so it's a horizontal movement unlike the previous one, and I'm going to go to the right 3 units. Let's see, number 3, I've got a multiple of 3 on the outside, so that's a vertical stretch. And I'm going to multiply all the y-coordinates by 3. Let's see, this 4 is multiple. It's a multiple of x. It's not an additive of x. It's a multiple of x. So it's what we call a horizontal compression. And we're going to divide each of the x-coordinates by 4. Okay, this +1, again, it's attached to the x, just like this -3 was up here. And so I'm thinking I'm going to move to the left, let's see, 1 unit. So anything that's an additive is always some kind of shift, versus anything that's a multiple is going to be a stretch or compression. And speaking of which, we've got a multiple of 1/2, so this is going to be a horizontal stretch, and by a factor of 1/2. So we're going to, let's see, divide each of the x-coordinates by 1/2. So it's very important just to keep talking yourself through these. Let's see, we've got a multiple of 1/3, and so that's a vertical compression. And we are going to multiply each of the y-coordinates by 1/3. And then last but not least, we've got this -6 just dangling at the end. And so we're going to shift everything down 6 units. All right, we're going to try to finish real strong with our big bear here at the end of the video tonight. And our goal is to try to rewrite this exponential function in standard form. And your first thought should be, well, I need a refresher on what is standard form. And we want our function to look like this: a times b raised to the x power, and then maybe a little plus c over there where the plus c represents the vertical shift up or down. And the first thing I'm going to do is I'm going to try to decompose this exponent, and that's because I noticed the plus sign up here. So my first thought is that f of x is really 3 raised to the 2x times 3 raised to the first. And certainly we have an exponent property. This is probably in the reverse order that we're accustomed to using it. But typically I might give you this expression and ask you to simplify it, and you say, well, if I'm multiplying two terms with the same base, then I would add these exponents, and that's where the 2x plus 1 came from. Well, in this case, we're doing just the opposite of that, and so we are decomposing the exponent is the terminology we'll use. And I'm going to try to clean this up. Let's see. This is actually my a value, so I'm going to put that in the lead. And then this is my b value, so I'm going to wrap him up with parentheses. He's being raised to the 2x power, and then we're going to subtract 2 later on. So let's see. So we're going to let this be my a value, that's my b value, and this is my c value, and so we are in what we call standard form. Now, who's the parent function that's involved here? Well, the parent function is going to be y equals 3 raised to the x. And that's I guess the original function upon which all of these multiplications and additives are being performed to. And as far as identifying two critical points, that's just really any two nice points that the function passes through. And I'm going to say 0, 1, as well as, I'll go with 2, 9. But really, as far as critical points, you can just pick any two out there, and then the asymptote is at y equals 0, just like the same asymptote as 2 to the x. All right, let's keep things moving if we can. They want me to describe the graph of f of x as a transformation of its parent function. Let's see if I can get this. Try to slide that graph down. All right. So let me recall what f of x looked like after we rewrote it in standard form. We had 3 times 3 raised to the 2x minus 2. All right. So as far as there's 3 different transformations taking place, and as far as what order they go in, I want you to imagine yourself trying to evaluate something like f of 10, where maybe you substituted a 10 in for x, and you're asking yourself, okay, if I was to evaluate that by hand and try to come up with a numerical value without using my calculator, what order of operations would I do that in? And I think the first thing you would do is you'd multiply the 2 and the 10 together. So this is my first order of business, and that, ladies and gentlemen, a horizontal compression, because remember we're multiplying x, by a factor of 2, which implies that we're going to divide each x coordinate by 2. The next order of business, after I do 3 raised to that power, is now I'm going to multiply by this coefficient of 3 out here. And what that is that's going to be a vertical stretch. In other words, we're going to multiply each of the y coordinates by 2. And then last but not least, this minus 2 dangling at the end is a vertical shift. Big difference between a shift and a stretch, of course. And in this case, we're going to subtract 2, or in other words, we're going to move, I should say subtract each y coordinate by 2, and we're going to move everything down 2 units. So let's see, what I'd like to do is take those 2 critical points that we started with earlier and see if we can't keep track of them. So let's say we started with 0, 1, right? Well, after I divide each x coordinate by 2, it's still 0, 1. And then, so I'm going to check that off. And then after I do a vertical stretch, I'm going to multiply the y coordinate by 2, so now it's 0, 2, check. And then last but not least, I'm going to subtract 2 from the y coordinate, so I did all that work just to end up with 0, 0. Now the other critical point we identified, and that could be any point on the graph, is 2, 9. So the first thing I'm going to do is divide the x coordinate by 2. So now I got 1, 9. The next thing I'm going to do is multiply the y coordinate by 2. So now I've got 1, 18. So this one's a little more exciting. There's more action. And then the last thing we're going to do is subtract each of the y values by 2. And so now I got 1, 16. And I would plot that point. And last but not least, let's keep track of that asymptote. If we divide the x coordinate by 2, it doesn't affect the asymptote. If we multiply the y coordinate by 2, it doesn't affect the asymptote. But if I subtract by 2, guess what? Now the asymptote's at -2. So let's see if we can graph these 2 points and that line and put it all together. Let's see, we got, I like to do the asymptote part first, get that out of the way, label it. Well, then we've got 0, 0, and then I got to try to squeeze in, whoa, well, 1,16 is not going to fit on there very nice, is it? So we'll kind of fudge it a little bit. And then this graph is going to shoot up like a rocket. Sometimes my exponential functions don't look the prettiest, but we'll make sure it goes through 0, 0 and 1,16 with that asymptote. So ladies and gentlemen, nice job hanging in there, and we will catch you tomorrow.